We'll do the analysis of tapering bar here. So this is how a tapering bar will look like. So this is the side view, and three-dimensionally you can see that this is how it will look like. So you can see that this is actually a tapering bar with circular cross section, a circular cross section which is differing as we go down the length here. So now this is called as conical tapering bar. Also I can call this a circular tapering bar because its cross sections are circular here. And the other kind of tapering bar will be for which the cross section, if you see its cross section is rectangular, so I can call this a rectangular tapering bar. So this is how it will look like. So in this analysis we'll see three things. We'll see the stress, we'll see the strain, and we'll see the elongation. First we'll see for the conical tapering bar, then we'll see for the rectangular tapering bar. Now starting with the conical tapering bar, this is the side view, and its front view will get a circle here, and even the rear end also will get a circle. So diameters are differing. Let's take this diameter as small d, and the outer diameter, let's take it as capital D. Alright, so now from this tapering bar I'll take a section. I'll take a section here of very small length. Let's take this length as dx. The total length for this tapering bar is L, and this section is at some distance x apart from this end. Now we'll find out what will be the diameter at this section. Since this section has very small length, so I can consider this will have a uniform diameter, and its diameter can be written as, let's take this is capital dx. That will be equal to d minus d by L into x. So this is the relation we get. Now this d, that is the bigger diameter, minus this I can write, I'll instead take this as a constant k. So d minus kx. This will give me the diameter at any section in a tapering bar. Now if I apply some tensile force here or compressive force, say the magnitude is P, then we'll get some stress also at all the cross sections. So at this section if I have to find the stress, that is sigma, that is P by A, force by area. So the force is P here, and the area is given by this relation pi by 4 d square. We know this. So here, since the section has diameter capital dx, so I can take P by, now this 4 I can take it up here at the numerator, so 4p by pi into dx square. So this will give me the stress at this section. Next we'll see the strain, that is E, and we know that sigma, the stress, is equal to strain into Young's modulus. So the strain E will be equal to sigma by E, and sigma, what we got here, we got 4p by pi dx square, and that should be multiplied with E. So I'll get E here, so I can write 4p by pi into E dx square. So this will give me the strain at the section. Then the next one is the elongation, that is del L, and for this we'll use this relation, strain is equal to del L by L. So del L will be equal to E into L, which means I'll be getting here 4p, the strain, what is the value of E? 4p by pi E dx square into L. So I'll be getting L here. So this will give me the elongation at the section. Now if you see the length of this section, this is the length of this section, isn't it? So this length is just dx. So I can replace it. I can write, instead of L, I can write dx divided by pi E dx square. So this is the elongation for the section here. Let me take this section as xx. So I can write the elongation for this section. Here I'll mention x here to represent that this elongation is for this section. Similarly, even here I can write x. Even the strain also I'll mention x here. And for the stress also I'll mention x here. Now the total elongation of this entire bar, it will be, I'll mention this is del L, which will be equal to, it will be the integral of the elongation of this section, that is del L x, and the limits I'll set from 0 to 1. So here at this point the length of this bar is 0, and here the length of the bar is L, so the limit 0 to L. Now applying the integral, I'll be getting this will be equal to 4p L divided by pi e d into d. So this will give the total elongation del L. Now instead of having a conical bar, if I have a cylindrical bar where you can see the diameters, even here the diameter is d and here also the diameter is d. In that case, the total elongation will be equal to 4pl by pi e into d square. Now for the rectangular tapering bar, you see this is the larger breadth at this end, and at this end we have the smaller breadth. So larger breadth I have taken as capital B and the smaller breadth I have taken as small b. Now here if I take a section here, so this section, say the length for this section is dx, and this is at some distance x apart from this end of this tapering bar, and the total length of the tapering bar is L. Now what will be the breadth for this section? So for this section the breadth will be bx. I'll write this, since the section I'll take this section as xx. So for this section it will be b minus kx, where k is equal to b minus b by L. So this will give me the breadth of this section. Now next is we have to find the stress for this section. And the stress for this section, let me write as sigma. Alright, so this is, since this is section x, I can write sigma x. So this will be equal to P by A. And I'm applying some force here, some force P. So that is there, and the A, that is the area, will be equal to the breadth into the thickness. So here you can see that this is the breadth, that is b minus kx, and the thickness for this is t. So I can write b minus kx into t. So sigma will be equal to, sigma x will be equal to p divided by b minus kx into t. Now after this we'll find strain, that is E for this section, so Ex. So this will be equal to P by AE. This is the relationship. So this will be equal to P divided by, I can write E into T, B minus Kx. So Ex is equal to P divided by E into T, B minus Kx. Now what will be the elongation? Elongation, that's del L. So E is equal to del L by L for the section X. So del L x will be equal to Ex into L, which will be equal to Ex is P divided by E into T, B minus Kx into L. Into L will come here, and instead of L I'll write this. You will see here that the length of this section is dx. So instead of L I'll write it as dx. So this will give the elongation for the particular section. What will be the total elongation then? Total elongation, as we have done in the last case of circular, that is conical tapering section, just like that, even for this also we have to take the integral now. So integral integral, the limits will be from 0 to L, since that is the length, into del Lx. So this will give PL by ET B minus B log B by B. So this relationship will give the total. This is actually for the total elongation del L.